All right, let's start. It seems we always have fewer students on Thursdays. And so today, in today's lecture, we are going to cover the second part of levels of testing, and we will learn a bit about how to automate the testing process. And this is today's outline. So first, we will learn about system testing, and we will learn different some popular or some majority types of system testing, and then we will learn test automation and scaffolding. So before we jump into the content, let's have a quick recap of what we have learned so far. So in our last 2 weeks, we have learned functional testing and structural testing, and they help us to design test inputs or test suites. And in this week, we started to learn different levels of testing, which helps us to determine the testing target given a very big piece of software. And in our last lecture, we have learned unit testing. So the key thing here is that unit testing is normally done by the developers during development. And we also learned about integration testing. And the key of integration testing is about how do we build different types of integrations. And today we will continue to move one level up to learn system testing. And the key of system testing is that in our last lecture, we actually learned that system testing is somehow closer to functional testing because we are testing against, we are testing the entire system against the requirements. However, there are non-functional testing for system level of testing as well. So we will learn some of those testing techniques. And we learned how to design test inputs and test suites in our last 2 weeks, and we learned how to choose the proper testing target in this week. So after this week, we will move on to individual testing techniques or some specific techniques. So first, let's have an overview of system testing. And this is some kind of boring definition again. So system testing is basically the testing that is conducted on the complete integration of every component, or like the entire system. And this is to evaluate the system's compliance to requirements for both functional and non-functional aspects. So this is the definition of system testing, and here are some keywords in this definition. So the first one is the target here is the completely integrated product. So we are testing everything together, and what we are testing against is the specification or the requirements. And these requirements could be functional or non-functional. So we could have some non-functional requirements for system testing. And one of the most obvious or significant characteristic of system testing is that it is, from the 3 different levels of testing, it is closest to our everyday usage of the software. So we are more like testing how the software would be used in the daily usage scenarios. And as from the definition, we can see that system testings could be categorized as functional or non-functional. For functional, we are actually kind of familiar because we have learned a lot of different functional testing techniques in Week 2. And so for functional testing, normally what is tested is here, like all the features of the target software, the business logic, and of course, the interactions between different individual components inside the system. And the testing method is like we provide the input and we validate the output against expected results. So this is normally what we do for functional testing, and we have learned that in Week 2. However, for non-functional testing, what do we want to test? We want to test some properties of the software or the system that are not related to the usage or the functionalities of that software. So what we care here are the performance of the system, the scalability of the system, the usability of the system, and many other quality-related attributes. And the testing method is also different for non-functional testing. So because we are introducing many more different attributes, we need to somehow measure them, and we need to benchmark them and evaluate all these testing methods based on some predefined criteria. So you may get confused about, okay, that's all about the definitions and some theoretical comparison. So you may, let's have a look at an example to see what's the difference between functional and non-functional testing. And we can use the example of the tram system here in Sydney. And this photo was not taken by me, but I like this photo because we can see the keyword test in this photo here. And for functional testing, in this tram system, what can we think about? What are the features that we can test for functional testing? So here are some examples. So we can test the scheduling system of the tram, and that is related to the usage of this system. So we can test whether the train services are running according to the schedule or not, and this is considered as functional testing. And another feature that we could test for functional testing is about the passenger information system. So we know that on the tram we can get information on some screens or through the broadcasting. So we can test whether the information display or the information is correct or not. So or if it is accurate or not. So this is also considered as a functional feature. And for non-functional features, according to our definition just now, we can test more about scalability or performance or usability. So for tram, one of the easiest thing we can think about is about scalability. So we can test how well the system handles increased number of passengers during some festivals or some peak hours. And we can also test about maintainability for this entire system. We can check whether it is easy to perform maintenance tasks or not. So all these, as you can see here, all these non-functional testing scenarios are testing some corner cases that are not covered by the daily usage scenarios. So basically for functional testing, we care more about how the users or how the customers would use the system in their daily usage. And for non-functional testing, we care more about those extreme cases or those rare cases that are not related to the daily usage of the software. So this is a rough idea of how do we differentiate functional and non-functional testing for system level of testing. And let's do a live poll and see if you can understand the concepts or not. So let's consider, is the property or the feature of security is considered as a functional feature or a non-functional feature? Okay, we only have one student here, so I don't know if anyone is watching the live stream or not. No, it seems we won't get more responses. But you are correct, you are correct. It could have both, it could be both. Because actually in most of the text or most of the materials you could get from the internet, security is normally considered as non-functional feature. Most of the time it is considered as non-functional feature, but it could also be a functional feature. And the reason is that there are some rare systems where security is a feature of that system. So for example, for the autopilot system of those autonomous vehicles, security is a feature and is related to daily usage. So for those systems, security is considered as a functional feature. But for most other scenarios, security is considered as a non-functional feature. And security testing is considered as non-functional testing. And let's continue. And here is a more formal comparison of functional and non-functional testing. So for functional testing, it actually normally involves testing the product's functionality. And for non-functional testing, as we have seen just now, it cares more about the quality of the product, and the failures captured by functional testing and non-functional testing could also have a little bit of difference. And the stage when we do functional testing and non-functional testing are also different. For functional testing, we could do it at unit level, we could do it during integration testing, and of course we can do it at system level. But for non-functional testing, normally it is only done in system level of testing. And for functional testing, to do this type of testing, only the domain of the product is required. So we don't really need to know more like how to deploy the system or the environment of the system. We don't need to know those kind of knowledge. But in order to do non-functional testing, because we have to cover some rare usage scenarios, we have to know more about, we have to have more knowledge about the target. And for functional testing, because we don't care about, normally we don't care about the environment of the software we are testing, so we could keep the configuration the same for functional testing. However, when we do non-functional testing, normally we will need to tweak the configurations of the system. And since we have learned that system testing could be categorized as functional or non-functional, let's learn more about functional testing first. And one of the most typical type of functional testing is called model-based testing. And if you have learned about, if you have learned formal verification, you have taken that course before, you may have heard about model checking. And this is somehow related. So model-based testing is actually to describe the system as a model, as an abstract model. And we test based on, we derive test cases based on the model we have created. And this model here is an abstract model, so we can simplify the behavior of the system. And the second, actually, there are some more things we need to take care about. So the model actually captures the behaviors and structures of the system. So we could have models to capture both. We could have models to capture either one of them. And a model is normally considered as an abstraction of the system being developed. So we can abstract away unnecessary details so we can perform more powerful analysis. And models, because we can use it to capture both behaviors or structures, so we could derive models from the specifications, the requirements, or source code sometimes. So we can derive from both requirements or implementations. And actually, we have, because system level testing is, we are now learning functional testing, and one of the typical type of functional testing is model-based testing. And we have actually learned one requirement-based model. So can you think about what was the model we have learned? You have seen the slides, right? No? Okay, good. So can you make a guess? For functional testing, we have learned something, right? We have learned boundary value, we have learned equivalent class, we learned decision table, and we learned cause effect graph. Yes, actually decision table and cause effect graph, both of them are the model we could derive from requirements. So here are some typical models we will encounter if we want to do model-based testing. So the first one is called finite state machine. And many schools or many universities, they use this type of finite state machine to teach some testing courses. And finite state machine is actually, have you heard about it before in other courses? No? Okay, it's like an automata that can be used to generate, to describe different states and transitions between states. And because it could be represented using a graph here. And each one of the node in this finite state machine or in this graph is considered as a state. And the edge is considered as the transition between states. And we can label the edges to represent or to describe the actions that will lead to the transition there. And this one here is a very simple state machine to describe the coin used for some lockers. And another typical scenario that we could use state machine, we can actually use state machines to describe almost any programs we have nowadays. For example, you can use state machines to describe the behavior of a vending machine. So maybe the default state of the vending machine is like waiting for users to press buttons, and if the user presses a button, it goes to the next state, and so on. And another scenario is like the ATM. So the default state, of course, is to wait for inputs, and then it will act differently according to different inputs and run into different states. So almost all the programs could be described as a state machine, but for model-based testing or for model tracking, sometimes we have to use finite state machine, which is to limit the number of states to be a finite set. And that's too much of the details here, but we just need to know that, okay, there is such a type of model in this course, so we don't look into too much of details. And another graph-based model is called Petri-net. And this is actually named after the computer scientist who proposed this type of graph. And it is also a graph-based model that is similar to state machines, but is more complex or more complicated. So each one of the nodes in this graph is actually a place, and either a place or a transition. And it uses transitions to transit from places to places. And it also, you can see there are some dark dots inside the place, and those are actually tokens. So it can transit tokens from one place to another. And this is more complicated than finite state machine, and we rarely encounter this nowadays. But it was popular because it can help us. It actually can help to capture workflows sometimes more accurately than finite state machine. So this is called, this is the second type of models you may encounter when you do model-based testing. And the third one is called context-free grammar. It is not a graph. It could be described using a graph, and it's not a graph. It could be described as some kind of language, a domain-specific language. So it is used to describe a system's input and outputs. So to describe the structures of those input and outputs. And context-free grammar could be used to describe code. Could be used to describe programming languages. So that's why it is actually ideal for testing compilers. So we can use context-free grammar to help us to generate some simple code, or to test compilers and interpreters, or the parsers of those compilers or interpreters. So this is context-free grammar. And here comes our old friend, decision table. Okay, so hello, decision table, my old friend. So have you heard about this song before? Do you know this song? No, this is from an old movie. And hello, darkness, my old friend. Okay, I won't sing it here, but decision table here is actually what we have learned, and why we need to do it, to mention it here again, because I observed some pitfalls from some of your questions about this easy assignment with decision tables. So actually there are two main types of pitfalls I observed. So the first one is you may just, some of the students I think may just try to focus on the actions of decision tables, or try to group conditions or rules based on the actions. And if you are watching the recording, I hope you watch this recording before submitting your assignment 1, because this might be related to your assignment 1 questions. So the first type of pitfall is that you may try to focus just on actions, and however, decision table is more like is used to describe both causes and effects. So we should also think about causes, not just the effects. And later on we can see some more examples about this. And the second thing is, some students, you may try to make all conditions binary. This is doable. So every condition could be somehow converted to a true or false, yes or no question. But sometimes we have to avoid making our conditions binary. Some of the conditions, they are naturally having multiple choices. So let's try to explain some of the pitfalls with some more examples. So let's imagine for an extreme case. Imagine we have a very big QA system that in this system only have two types of outputs, yes or no. So let's imagine we have a very complex system that can answer any question, but it will only answer with yes or no. So it will only answer with yes or no. So let's give it a test case. So this is actually a test case generated from some conditions. So is COMP3142 a good course? And let's assume the answer is yes. Let's assume the answer is yes for this question. And we could also have another question based on some conditions. That is, like, let's say, is Sydney in New South Wales? And of course, the answer is yes as well. Since both answers are yes, can we group the conditions behind these two test cases together as one rule? Definitely not, right? We cannot only have two rules for this complex system. We cannot only have two rules for this complex system because we need to generate a test case according to the rules. And we can't simply we can't simply do the rule grouping just according to the final output. So what can we think, what's the thinking process here? So the first question is more like some type of, although this system could accept any type of questions, but let's try to consider how the system works. So the first question is more like a reasoning question. So it requires the system to do some reasoning. And the second one is just checking some facts. So internally, this question should get to the reasoning system and generate a yes. And internally, this question goes to the fact-checking subsystem. Let's imagine it has such a system here. So this one goes to the fact-checking system and also generates yes. So although the final result is the same, we cannot put them together, we cannot merge them together because the causes of the effects are different here, according to the semantic of this system. So this is just an extreme case where we have a very simple output, but we have very complex inputs. So when we do this kind of grouping or merging, we have to think about not only the effects, but also the causes. And for the second pitfall, trying to make our conditions binary. So let's consider this example here. This is actually somehow similar to some conditions in assignment 1, but since not many of you are here today, and so it's not considered as making the assignment easier, I believe. And so let's consider this scenario. Let's try to consider a program that helps us to check the validity of postcode in Sydney. And actually, in reality, Sydney has several different ranges for valid postcode. And one of them is in between 2000 and 2599. And let's consider we have this validation program. It will generate whether, it will try to check whether a given number is a valid postcode for Sydney or not. So it will tell us whether a number is a valid postcode or invalid for Sydney or not. So we could have 3 different ranges for postcodes. We can have it this range, we can have this range, too small, too large, or valid. So these 2 are invalid. This one is valid. And we can make every one of them a true, false, a true or false condition here. And you may think, okay, but we can also have a condition for P code, for post code, and allow it to take the value of A, B, and C, right? We can make it a non-binary condition here. We can also do this. And making it a non-binary condition can actually help us to reduce some of the redundancies, like some of the rows and even columns in the table. But you may try to argue that, okay, can we, since both of them are related to invalid behavior, so can we merge these 2 conditions together? Can we do this? Can we have this? P code is smaller than 2000 or larger than 2599. And this will still goes to invalid, right? This condition here. But, But it's not encouraged to do this, because if we use these 2 conditions with binary choices, we will have 2 rules eventually. And when we generate test cases with this condition here, we can generate one rule. We can generate one type of invalid input. It's either the postcode is too small or it's too large. So we are missing one of the conditions here when we try to generate test cases, if just based on this binary choice condition here. So that's the drawback of having this instead of having a multiple choice condition here. So that's the thinking behind this example. So you look confused? Is it clear or not? The missing case is if we use this one to be true, false, right? If we set this one to be a binary, then because this one could be true if any of the condition here is satisfied, right? So if we choose the P code to be smaller than too small, then we are missing the test case for P code being too large. So that's why we will miss one test case here if we just make it a true or false, and if we just merge these 2 conditions to be a true-false condition here. And because we are thinking about both effects and causes, so we can't really merge them here because we will miss one of the potential behaviors of the program. So that's why we can't do this for this example. For the assignment, you have to think it for yourself. And let's continue. So another type of just now all the models could be derived from requirements, and there's another model that is quite important here that could be derived from source code, and it is called a Markov chain. And Markov chains could be derived directly from programs. For example, for this one here, we can have this Markov chain. So Markov chain is actually similar. You can consider it as similar to finite state machines. So each one of the node here represents a state of the program. So this this one here represents the state of the program before the first if, because this string cannot pass the first if. This one represents the program state after the first if, and so on. So each one of the node here represents a program state, and each one of the edge here represents transitions between program states. And you can see there are some numbers on this edge. It actually represents the probability of transiting from one program state to another if we randomly provide inputs to the program. So let's have a look at some examples here. So remember, the numbers here are the probabilistics of transiting from one state to another if we use random program inputs. So for this program, if we use random inputs, a 4-byte string. So y this number is, y jumping from here to here is 2 to the power of minus 10. So let's try to reason behind this. So the reason is that if we try to jump from this state to this one here, we have to make the first byte to be the letter B here. And we need to do it in 2 steps. The first step is to choose the correct byte to change. And choosing the correct byte is 1 divided by 2 to the power of 2. 1 divided by 4, actually, because we have 4 bytes. And that is 2 to the power of minus 2. And once we have selected the correct byte, we have to make it the correct letter. And because 1 byte has 8 bits, and each bit could be either 1 or 0, so we have 2 to the power of 8 choices. And if we want to make it correct, we have the chance of 1 over 2 to the power of 8, 2 to the power of 8, and that is 2 to the power of minus 8. And in the end, we have 2 to the power of minus 2 times 2 to the power of minus 8. And that is 2 to the power of minus 10 here. So that's why we can use Markov chains to capture program behaviors, especially during random testing. And this one here, of course, is also obvious. If the program is here, and we supply the program with another randomly generated string, the chance of staying in this program state is 3 over 4, because we just change either one of these here to stay in this state. So, but this is not very accurate. We need to minus the chance that we make A correct in this edge here. So this is not very, very accurate. But you roughly get this idea. And this, because this could be used to capture the behavior of programs during random testing. And this is effective for fuzz testing or random testing, and it could be useful for your assignment too, because some of the advanced algorithms are developed based on this model. And actually, this figure is actually from one very famous paper in this field, and we just identified an error in this paper just now. Yeah, this should be 3 over 4 minus the chance of getting A correct. So that's Markov chain. Because sometimes the programs have to reach certain program state to trigger some crash or errors. And if we know about the probability of jumping from one state to another, we can somehow calculate the effort of getting from one place to another. And we can somehow use it to do some estimation of how many test cases do we need, or how to evaluate the the value of different test cases. So this is why we care about probabilistics here. But we will learn more later about this, about random testing and fuzzing. And that's all about functional testing or model-based testing. And and before we start, let's have a 10 minutes break. All right, let's continue. So we just learned about model-based testing for system testing, and now let's continue to learn some non-functional testings at system level. So for non-functional testing, it involves, just now from the comparison we could see that it often involves more time, effort, and resources. And the key here is to set up a proper configuration to conduct the testing. And that is to get a proper environment that is closer to real life to simulate the extreme cases of the potential usage of this system. So there, of course, we have to, when we do this kind of configuration or environment setup, we need to think about all these behaviors, all these specs of the customer's environment in advance. We have to do that before we have to assume the customer's setup when we do this kind of configuration setup. And normally when we do non-functional testing, because we are trying to evaluate the performance of the system under limited resources, normally we care about these 4 types of resources. So we care about CPU usage, we care about disk usage, we care about memory usage, we care about network usage. And if you are using a Windows system, you use Task Manager, you can see all the tabs in the Task Manager, and these are the resources we are interested in when we do non-functional testing. However, is there anything else do you think we need to care about here? Any other resources? What? What other resources do you think is possible to consider nowadays? Because this is actually from the textbook, and all the textbooks are very old. And now we need to care more types of resources with some emerging software, new emerging type of software. GPUs, we need to care about GPUs. And in fact, in the latest, in Windows 11 or Windows 10, I think, starting from maybe Windows 7 or Windows 10, the Task Manager can show the GPU usage as well. So, because we need to run those AI models, so they are normally running with GPU. So there are many different types of non-functional testing. And the first one is called performance testing. And this is a big category of testing techniques. And under performance testing, the first type of testing we can do is called load testing. It is actually related to how the system behaves under expected load conditions, under expected workload. So this is like testing the system with a valid range of workload. And an example here is we can test web CMS by simulating 500 concurrent students accessing maybe the same page, because 500 is a normal size of class here in USW, so we can do this kind of testing. And the second type of performance testing is called stress testing. And it actually evaluates the system's behaviors under extreme conditions beyond the expected or the designed maximum load. For example, a news website could be designed for, let's say, 1,000 users to access simultaneously. And we can somehow simulate we can increase the user count to 10,000, and to see what the system will behave when a breaking news comes out. So this is called stress testing. It is like testing the robustness of the workload. Let's continue. So apart from load testing and stress testing, we also have spike testing. So spike testing doesn't deal with the absolute number of workload. It deals with drastic changes of workload. So we are more interested about how the system will behave when there is a sudden increase or a sudden decrease in the number of users. And an example is like this. So we can test web CMS by generating a sudden spike of 1,000 students maybe submitting to their assignments before the due date, to test how the system, how robust is web CMS. But I don't think in real life web CMS can handle that with the current server. And let's continue. Apart from spec testing, the last type of performance testing we are introducing here is called endurance testing. So it actually ensures the stability or the performance over an extended period. So this is normally just to run this program for a very long time. For example, we may try to run a video streaming service for like 48 hours and see what happens in the system. For example, for the live stream here in this classroom, what if it doesn't turn off after 3:55? So what will happen? Maybe it will record a very long video that use up all the disk space in the cloud server. So we should test these kind of scenarios. And based on my real life experience, some of the older versions of Chrome on Mac may have some kind of memory leak problem. So if you open the web page, especially those related to videos, like a YouTube page, if you don't close that tab, Chrome will gradually use up all your memory. And that is because of a memory leak. They don't do the garbage collection effectively. So that's a real life experience. And apart from those performance testing, we can also do scalability testing. So the definition of scalability testing here is that we need to test the system's capability of scaling up or down when as per the demand by adding or removing resources. So the key word here is about resources. So we change the resources provided to the system and observe how it scales up or down. So an example here is we can try to test an application running on cloud service by gradually increasing the number of application servers and database instances and see how it deals with increasing number of users. So we modify resources here. And normally this is done for cloud services because in some of the cloud service providers, they provide elastic instances to allow you to scale up and down according to the current usage. And this is especially useful for you to save your budget if you are running a cloud service. So this is normally done for cloud services. And you may wonder what's the difference between scalability testing and stress testing or load testing, because they are also dealing with increasing number of users, right? for scalability testing, for stress testing and load testing, we don't modify the resources provided to the system. For scalability testing, we normally update the resources as well and the number of users. So that's the difference here. And apart from performance testing and scalability testing, we also have usability testing. And the definition is like this. So we assess how easily different groups of users can learn and use the system. For example, we can evaluate a healthcare app given to a group of doctors and see if they can navigate through the different pages, and the feedback is collected to improve the UI and UX design. So for this type of usability testing, it actually deals with human. So it is actually related to HCI topics. So there are HCI courses here provided in UNSW, and if you have taken one of them, you may consider how to design usability testings. But normally usability testing is related to human and is kind of subjective. And sometimes if we have some special user groups, we may also consider the accessibility of the system. So that's the usability testing. And we also have another type of testing called compatibility testing. So usability is dealing with users, is dealing with human, while compatibility is to test whether the system is compatible with other programs. So it cares more about the interactions between programs rather than the interactions between humans and computers. So an example here is we could test a mobile, because normally all the mobile apps, they have two different versions. One is on Android, the other one is on iOS. So we can test whether this mobile app is compatible on different devices or not. And of course, this is also done for web pages, because most of the web page design should be responsive. For example, for this one here, if we modify the screen size, it should be responsive, because different laptops or different devices could have different screen size. And another example here is some of the browsers even provide compatibility testing features to test whether your website is compatible to different screen size or different devices or not. So this is from Firefox. So you can see that we can try to view this we can try to simulate how this website will look on different devices with different display size. So we can do this, as you can see here. We can try to even rotate the device. We can select the type of device here, but it's not very up to date. I think it's only iPhone 13. But anyway, compatibility testing is mostly related to those mobile apps or web pages which will run across different platforms or different operating systems or even different devices. So this is compatibility testing. And another type of non-functional testing is called availability testing. So all these concepts, they have some minor subtle differences in their definitions, but you don't need to memorize all of them, but you just need to know that they are different and what are the differences. You need to know what are the basic concepts of these techniques, because if people ask you what is availability testing, you don't mix it up with usability testing, right? So for availability testing, it deals with verifying the availability of this system over time, or the uptime under some specific conditions, and measure the downtime. So for most of the cloud services, they are running, they are always running, so they shouldn't stop. And for example, an online booking system, it should be always available for the users, right? So another example is that even for Google, it sometimes faces availability issue. And the last availability incidents for Google happens 4 years ago, where all the services are not available for about 6 hours, if I'm not wrong. So even Google, they have very robust server clusters. They may still face the availability problem. And sometimes for web CMS, we may have availability issues if the servers in CSE are not running properly. So availability testing is important here to ensure that the service is always there when the user wants to use it. And there's a special type of non-functional testing which is called reliability testing. So remember, in our first lecture, we learned about software dependability. And one of the concepts related to software dependability is called reliability. So a software is considered reliable if it seldom makes errors, or it seldom runs into errors. So this reliability testing here is to test whether the system is reliable and performs consistently under a specific condition for a particular period of time. So reliability actually deals with all the previous properties we have learned, like availability, like usability, like the performance. So an example here is this page, but the key thing here is that when we want to observe the behavior or the performance of this system for a period of time. So an example here is a payroll system is to run continuously, maybe for a month. We observe during this month and see if it can correctly do its job. So this is reliability testing. And this actually overlaps with other non-functional testings, because the definition of reliability deals with performance, deals with availability and usability, and so on. And here is a more detailed explanation of how reliability testing overlaps with other types of non-functional testing types. So for example, the goal of reliability testing is to ensure that the system could perform consistently without failures during a defined period. And many of the non-functional testing types, like performance, stress, load, availability, are part of the definition of reliability. And the key focus for reliability testing is about the stability and consistency during that testing period. And and others. But this is a bit different. So other testing types, they don't really focus on the stability and consistency, but their properties could be used to contribute to reliability. So maybe for example, for performance testing, we don't run the program for a period of time and check if the performance is consistent or not. We just check whether how is the performance of the system under that condition. But we don't check whether the performance is consistent during a period of time. So this is the difference between reliability testing and the other non-functional testing types that has overlapping concepts. And the duration of reliability testing is often typically a long-term duration to access the stability. So, but for others, they may have a long-term testing, but normally they don't last very long. So that's the concepts. And to check if you have remembered what we have learned according to those definitions, let's think about these two examples here. So for the first requirement, it describes that the system that accepts the query for 1,000 records should have a response time less than 3 seconds. This is the first non-functional requirement. The second non-functional requirement is 25 client logins should be possible in a configuration that only takes 20 clients. So what are the non-functional testing techniques needed for checking these two non-functional features? Let's do a live poll to check if you can understand the... Oh, we have a lot of responses. I hope this is not... I hope you are watching the live stream, not just randomly do this. And I think most of you can get it correct. The correct answer is load testing for the first one and stress testing for the second one. Why it is not scalability testing for the second one is because just now we have emphasized the difference, the key word in scalability testing. We need to adjust. Normally we need, because all these stress testing, load testing, and scalability testing deals with the number of users, right? Or the number of usages simultaneously. But for scalability testing, we need to change the resources. We need to adjust the resources supplied to the system. So that's why, because the second one here, we don't adjust the results here. So it's not a scalability testing. And it is a stress testing because stress testing deals with the workload that is beyond the design of the system. And here it is quite clear that we want to track how does the system designed for 20 clients perform when 25 clients are using this system. So that's why. And let's continue. So that's all about the non-functional testing strategies. And let's learn about test automation. A little bit of test automation today, but it's not fully automated, still not fully automated. and test scaffolding. So we have covered many techniques to derive test cases in different levels. And how do you run them on the program is the actual problem here. So of course, once you have generated the test cases, you can run the code and check the results manually. But in the assignment, you have noticed that you may generate thousands of test cases sometimes. And that is not possible to do it manually. So please don't do this. Please don't run the program manually to do the testing, because humans are slow, expensive, and sometimes error-prone. So let's try to write programs to do this test automation. And another thing here is designing test cases or designing test inputs requires effort and creativity, because sometimes you have to reason about the semantics of the target system you are testing. So, but test execution should not require too much of effort and creativity, right? Because we just want to do some routine task for running those test cases. And here comes the concept of test automation and test scaffolding. So test automation is the development of software to separate the repeating tasks from the creative aspects of the testing. So what are the repeating parts? So here are some examples. So the control of the environment and preconditions before we do the testing. So we need to set up the execution environment for the target software. And that could be automated. And the second one is, when we execute the program, we should be automatically to tell if the program runs into some error or not, right? So the automatic comparison between the predicted result and the actual output could be done or should be done automatically. And the third one is, we need to be able to execute or re-execute the test cases, the tests automatically. So these are the aspects where we could automate the process of testing. And that's the concept of test automation. And test scaffolding is like a set of programs written to support test automation. And they are not part of the product, just like in the real scaffolds, they are not part of the buildings, right? When we build buildings, they are just supporters for us to build the buildings. So the test scaffolding is normally not part of the product, and is often temporary. So here is the structure of a normal test, or very common test scaffolding code. And here are some concepts. Here are some more concepts. But you may encounter these concepts. You may have encountered some of these concepts before, right? So do you still remember what is a driver, what is a stop, and what are the differences between drivers and stop? Because we have learned it in integration testing. And here the new concept is called a harness. A harness is actually, sometimes even in some research papers, people may mix up the usage of drivers and harness. And so it is kind of, the definition could be blurred sometimes, but let's try to make it precise in this course. So a harness here refers to a substitute of all the part of the deployment of environment. So it basically deals with the environment setup, like how do we direct the user input or the parameters to the target we want to test. So, or how to set up some preconditions prerequisites required by the target code we want to test. And the drivers and stop, for these two concepts, the definitions are the same, almost the same as what we have seen in integration testing. So a driver is like a substitute or a mock-up of the calling program or the caller of the target program unit we want to test. And the stop is like a substitute of the system functionality or the unimplemented. Maybe we haven't implemented a subsystem that is used by the target program unit we want to test, so we replace it with a stop. Or it could be represented as something that is not integrated yet during integration testing. So it is normally the callee of the program unit we are testing. And the third one here you encounter is called the test oracle. We will learn more about how to design test oracles later, but for now, you can just think of it as it compares the actual output with the predicted or expected output. So it's like telling us what is the ground truth, or telling us when the error occurs. And of course, the last part, this is most of the time this is optional, so we need to tear down the test case. And these are the steps that we need to prepare the entire system ready for the next round of testing. So sometimes, for example, if we are testing some databases, we may need to reset the data stored in the database before every round of testing. So this is called tear down code. So why do we need to learn this structure here? So the reason is that there are many, many different frameworks around to help us to do this kind of automation. And almost all of them follows the structure here. So if you know about these structures, once you are trying to use one of the frameworks, you can easily get started. So that's why we learn the basic structures here. And we are not particularly interested in a particular programming language or a particular framework here. So, but let's try to let's have a look at some of the most popular frameworks for different programming languages. So the first one, and most of the test automation or test scaffolding are the unit testing frameworks. Why do I put a double quote of the unit here? Is because most of the so-called unit tests we are doing in practice are more like integration testing, because we are not only testing a single function or a single method in those test cases. We may test multiple functions or multiple program units. So it's more like integration testing. And for Python, we have two very famous frameworks, PyTest or Nose2. For Java, there is one very famous testing framework called JUnit. For JavaScript, if you have taken 1531, you may have used Jest or Mockito. And for C or C++, we have Google Test or Gtest. And for Rust, because it's a new language, it has a built-in testing framework. So these are all the popular frameworks that to do test scaffolding. And let's see why they could be matched to the structure we have learned. So assume we are trying to test this program in Python. And the target we want to test is the calculator. And this calculator delegates the adding feature to another object, adder object. And this is some kind of redundant code, but let's just use this as an example here. So this is the target we want to test. And what we can do is, if we just want to do a pure unit test for calculator, not integration test, so what we can do is we can write a stub for the adder and assume that we haven't implemented the adder yet, or we just want to separate the testing of these two classes. So we could have a stub for the adder here, and then we can have these lines of code to do the actual testing. So this is an example test case for testing the previous Java program we have seen just now. And let's try to match the structure from this code back to what we have learned just now. So first, this entire thing here is like the driver plus harness. So if we want to be more accurate, we could say that, okay, the setup for the class, the creation of the class, the object, the stub, and the calculator object is the harness, and the actual calling location of the function we are trying to test is the driver. And let's try to find out the stub. And the stub is very obvious. The stub is named as stub in this example here. And we can also see we could have the output comparison. We should have the output comparison here using assertions. And in this example, we don't really have tear down. So this is the example using Python. And we could also have examples using JUnit. So let's assume we are testing a similar app, also called calculator. And this time, we can try to identify the key structures from the code of the JUnit test case. And we can see that in this case, we are annotating the functions. So annotations of functions are like wrappers of functions. So they are these two functions, they have the same annotators, which means that they are wrapped with the same code implemented by the JUnit framework. So they will behave similarly, these two functions. And as you can see, the annotation is meaningful. So this means that this after each means that this function will be invoked after each test. And this before each annotation means that this function will be invoked before every test. So can you imagine what does the before each correspond to? Stop? No. Harness. Sorry, I messed up with the order of animation, but anyway, so this one here is obviously tear down because of the name here, but it's also because it should happen after every test case. So it's tear down. Oh, I didn't put annotations for this page, but before each is harness. It's like setting up the environment. And this one here, the actual calling location here is actually it is put in one line with the assertions. This one here is the driver or the program unit we want to test. And the assertion here is obviously the output comparison. So we can find the structures in JUnit as well. And let's see gtest for C or C++. So this is C++ code. And let's try to identify different structures. So in this case, you can see this test F is actually a macro in C or C++. So these macros work similarly to annotations. It's like wrapping the function, this function around. So these macros are used to do the scaffolding, and I try to identify some key features here. So, for example, for setup, it corresponds to the harness. And for teardown, we can have this kind of teardown here, and this calculator test class inherits the public class of gtest. So it follows the behavior of the parent class. So we can do the teardown and setup with gtest, just like what we did with the before each and after each in JUnit. So no matter what framework or what language you are using, you can always find these structures. That's the spirit here. So you can also find that these expect equal corresponds to the output comparison. Those are some macros which are used for assertions. So you can always find these structures in whatever code you are writing. So that's all about test scaffolding. So we won't introduce you very concrete examples of how to write unit tests in a particular programming language, because you can find out how to use these libraries or frameworks from their documentations. But if you can understand this, you can quickly learn how to use all these libraries or frameworks. So that's the idea here. And before we end today's class, let's have a quick recap of what we have learned so far. So I'm trying to repeat this again and again, so you can memorize everything. So we have learned functional testing and structural testing in the last 2 weeks. And functional testing is black box testing, while structural testing is white box testing. Black box testing deals with checking against requirements, and white box deals with checking against implementations or source code. So, and both functional testing and structural testing helps us to design test inputs. And in this week, we learned different levels of testing, and different levels of testing could correspond to different stages during development. And they help us to determine the target to test. And the first level of and one of the key concepts here is the V model of testing. It actually captures or describes the correspondence between different development stages and different testing stages. And the first, if we go bottom up from following the V model of testing, we start from unit testing, where it is normally done during development by the developers. And normally a program unit is considered as a single function or a single method of the program. And we could apply all the black box or white box testing techniques we have learned, especially white box testing techniques we have learned, to design unit tests. And moving up one level, we are getting the integration testing. So in integration testing, we care about how do we build those integrations. So we have multiple ways of building the integrations. We can use program requirements to build the integrations. So that is functional decomposition tree. We can use that to build decomposition-based integrations. And for decomposition-based integrations, we can have top-down, we can have bottom-up, we can have sandwich. And each one of them has their own advantage and disadvantages. And after that, we learned about using source code or using the implementation to build up integrations. So what we learned is how can we build integrations based on call graphs. And call graphs are special types of control flow graphs, which cares more about the relationship between different internal procedures of the functions. So the accurate term here is internal procedures instead of functions or methods. So that's how, so we can use different approaches to derive integrations from call graphs. We can use pairwise integrations. So we can also do neighboring integrations. We can use neighborhood integration for call graph, and neighborhood could have radius. So by default, we use radius 1. So that's about using call graphs, and that's from the perspective of source code. And we could have some kind of design that benefits from both structure, both requirement and implementations. And in that sense, we are building some other type of integrations based on the I forgot. Do you still remember that? What is the last one we learned for? So we may need to go back to the slides later, but we do have something in between functional and call graph. And today we learned the third level of testing, that is system testing. And for system testing, we care more about functional versus non-functional testing, because non-functional testing could only be done in system level, at system level, most of the time, because it's not meaningful to do some non-functional testing at unit or integration level. However, for functional testing, we care about a special type of functional testing here in system level that is called model-based testing. And for model-based testing, we learn about different types of models. And many models could be derived from the requirements. And decision table is one of them. And another important type of model that could be derived from source code is called Markov chain. And it is used to capture the probability of transitions between program states. And you may encounter that later. And after that, we learn many different types of non-functional testings. And one big group of them is called performance testing. And under performance testing, we try to adjust the workload of the system. And if the workload is within the normal range, it is called load testing. If it is beyond the designed range, it is called stress testing. And we also learn about scalability testing, which deals with adjusting the resources supplied to the system. And we also learn some other types of testing, non-functional testings, which are related to different properties like usability, like availability, and so on. And that's all about the different levels of testing. And today we also learned about test automation and test scaffolding, because writing or designing the test inputs actually requires some kind of creativity. However, running those inputs, running those tests doesn't require that. So when you try to write this code, when you try to do this maybe one day in a company, so what should take you more time is how do you determine different values here, or how do you determine different checks here, instead of thinking about how should I run this program, how should I set up the environment for everything, right? So that's why we need to learn some knowledge about how to do this kind of automation or scaffolding. And instead of learning a particular framework, we learn about the structures that could be used or that appears in every one of the frameworks. And we introduced some new concepts here, like harness, like output comparison and teardown. And we encountered some old comparisons, like drivers or stubs. So that's all about what we have learned so far. And actually, that marks the end of all these general concepts about testing. And we will move on to learn some more specific testing techniques and some more specific concepts related to testing. And that's all. Thank you for coming. It's better because it's still recording, I think. So, so stub is actually could be used for. It is actually a concept in integration testing. That's first. So when we are, because for integration testing we try to integrate component by component, and if a particular component is not to be integrated yet, we replace it with a stub, even if the code for that particular component has been implemented. So that's So that's for the integration testing scenario, and sometimes we can even do testing. We can even write test cases before we implement everything. For example, when we do test-driven development, we may want to write test cases before we do testing, before we do the development, before we implement the actual code. And if we haven't finished the implementation, we can use stubs to mock up some of the components. That's just an example here to give you a feeling about how it works. And normally a stub is, because we must know the difference between drivers and stub. Stub is like the called by the target we want to use, we want to test, and driver is like calling the target. So in that example, because it's just an example, is we use the adder as a stub because it is called by the target we want to test. So that's why. Okay. Okay. Okay, thank you. 下周第5周嘛，第6周他们就可以去试着玩了，然后那个咱们趁那2周 set up 起来，跑，然后他们第8周跑一次内部的比赛，就是比如跑2程序，让他们去比一比，然后第9周加一个程序，第10周加一个程序，才有这么着。啊，你那个啥时候来的？
就下周一。
你得赶紧的。我不是你别来，我最近可没时间帮你大改。
没事，我